Electric motors have been around for a really long time, while gasoline engines are comparative upstarts, having been around since the 1860s. Thanks, Otto. The first appearance of something that could conceivably be considered an electric motor, at least sort of, was the electrical whirl, which was the product of Benedictine monk Andrew Gordon and published in, and for this I'm very sorry German speakers, Versuch einer Erklärung der Elektrizität, which roughly translates as an attempt at an explanation of electricity. This principle was then extended by Benjamin Franklin, who I think is also known for some other minor, unimportant things. Although it took a bunch of people all around the world and the invention of the battery before the good old man of technology, Michael Faraday, demonstrated rotary motion in something that we would recognisably think of as a motor. Motors are one of the really delightful discoveries that really demonstrate the power of collective research and development. Bits and pieces from researchers all over the world were required to get to the understanding of principles, and drawing all of that knowledge together that really was what finally got motors functioning. And I know it's untrendy in the modern age to be like, ooh, woo, science! But it's one of those many things that without all of those people working together, we'd quite literally be living in a very different world. One of my favourite snippets of information that I read in preparing this was that Emily Davenport, of the inventing couple Emily and Thomas Davenport, cut up her silk wedding dress to insulate the motor windings, which is some pretty serious commitment. The couple eventually went on to publish the Electromagnet and Mechanics Intelligenza, the first newspaper printed on a press powered by electricity. Science and news together, they are like our distant ancestors. The long and the short of this is that the basic principles of how motors work has been understood for a very long time. And until now, we've needed metal to build motors. Miles and miles of thin copper windings. But this year, that might be about to change. Motors might be about to get a hell of a lot lighter, smaller, cheaper, and easier to make. So maybe we should find out why. So we recently covered in 10, that's our weekly news roundup show, if you're new to the channel, the research of Dr. Dae Yoon's team at the Korea Institute of Science and Technology, who built and demonstrated a metal-free coil technology for motors. And you all asked us to go a little more in depth, so here I am, bringing the goods. Never say we don't listen to our audience. Well, some of our audience. I don't care how many times you ask, I'm never going to do an ASMR recording of me editing. I did write to Dr. Dae Yoon, but sadly haven't got a reply. So this is all my best stab and a yes, I know this is simplified. I know I often look like a cool science teacher, but this is not, in fact, Nanomaterials 101. Alright, so I was going to spend some time sitting down and writing a careful explanation of how motors work, because I suppose that's technically my job. But then I remembered that I'm phenomenally lazy and that I could, in fact, just take a look because it's in a book. So instead of me writing it, I could just read to you from, say, my 1910 edition of Electric Automobiles from the American Correspondence School. Even better, I could just get someone else to do it.
It is with the utmost pleasure and a spirit of boundless enthusiasm that I bring you another of our episodic journeys into the reading rainbow. Today's most extraordinary and edifying program is designed to ignite the imaginations of our learned compatriots through the splendid magic of the education. In this modern age of wondrous invention, where the marvels of the moving picture now grace our very homes, we all have the opportunity to be enlightened from the comfort of our very own living rooms. And so, let us take our volumes, adjust our spectacles, and be inspired. Let us today be transported by electricity and an explanation of the electric motor that powers even the very hackney carriage that may have whisked you from your equal franchise society meeting to perhaps the colony club that very same day. The fundamental principle upon which the functioning of all apparatus of this type is based is to be found in the fact that when a current of electricity is passed through a coil of wire surrounding a bar or other form of iron or steel, the metal becomes magnetic in proportion to the number of turns in the coil of wire and the strength of the current employed. Every magnet consists of a north and south pole, and like poles repel, while unlike poles attract one another. In other words, if two small common magnets are placed on a table with their poles facing one another, and the magnets will tend to repel one another, and, were they sufficiently powerful enough, would actually recede from the common center until the limits of their fields were reached. By reversing the polarity of the opposing ends of the magnets, they would then tend to be drawn to one another until the poles butted. This, in brief, sums up the philosophy of the electric motor. In order to amplify the power, a large number of magnets are employed and in.
Okay, so I cut off there because, yes, that is the basic principle of electric motors. Basically all of them. A magnetic field, in this case created using electricity passing through a coil, interacting with another magnetic field, in this case from a permanent magnet, to produce motion. A commutator and brushes in this case are used to reverse the current's direction and create rotation. And back in 1910, basically the only option for powering your EV was your permanent magnet DC electric motor. Not because AC motors didn't exist, but because the technology to build small AC power supplies which could convert from DC sources did not exist. And to be honest, we still do use permanent magnet motors a lot today. And while the majority of modern mass-market EVs use AC motors, permanent magnet DC motors are still found in things like golf carts and budget-friendly EV conversions, and permanent magnet AC motors are found in all sorts of EVs. I'm not going to go deep into the many sorts of different motors. I promise. I did actually start down that path, and once I'd explained the general differences between AC and DC motors, and then started to get into permanent magnet synchronous motors and induction motors and switched reluctance motors, I realized that it's a whole video in itself. And one for which we would really need a long run-up, and one for which we'd need lots of time for Erin to do diagrams. Or perhaps we could clone and quick grow more Erins so they could work in parallel.
They're like huge seed pods.
I'll have to talk to Nikki about when the cloning pod is next available. As an aside to the aside, if you want more animations in these videos, which, based on your comments, it seems that you do, given that we don't actually have an easy way to vat grow more Erins, please go donate to the channel and share our content widely and help us grow, and we can get more Erins and animate the hell out of things. But the fundamental thing that's really important to get to here is that regardless of the type of motor, up until now, they've all been reliant on coils containing a massive amount of copper. The typical figure quoted is that EVs contain around 180 to 200 pounds, or around 80 to 90 kilos of copper. Although those figures are kind of old, and it's possible that newer models with weight savings might be somewhat lighter. But at any rate, a big chunk of that is going to be in the motor windings. The rest is mostly in the loom, although there's also often big chunks of copper used as bus bars too. And there's been much angst. So very much angst about whether the world can supply the copper required for producing the number of EVs we need to transition the fleet to cleaner transportation. You know, we could invest in public transit and walkable cities too. If we built e-buses and trams and light rail and urban centres that you can live in without a car, we could use way fewer resources. We could not just build massive EVs that... Oh, damn it. Sorry, I was in Europe on vacation and I got these foolish notions, you know, a society that works for the good of everyone, shared responsibility, government that supports the people, you know, socialist. Not socialist? No, okay. Sorry, I'm getting a notification from our bias observer from the Ministry of Public Enlightenment and Propaganda. Let me correct that. Communist. Yeah. Communist. I've been getting these terrible communist notions in my head. Give me a few weeks and I'll be okay. I'll be back to shouting drill, baby, drill again. Alright, so the TLDR is that Dr Dae Yoon and his team did two really important things. They did a better job purifying nanotubes, and they've come up with a way to make the windings out of carbon nanotubes instead of copper. Carbon, as I'm sure you don't need me to tell you, is much more abundant and easily available than copper. So, who did this work? How does this magic work, and what does it all mean? Well, first up, the who. This work, like I said, done by Dr Dae Yoon, and as I said earlier, he's at the Korea Institute of Science and Technology. Established in 1966, KIST is tasked with solving South Korea's national challenges, including social and technological ones, with the intention of providing South Korea with growth opportunities through research. So cue the whining from Western governments in a couple of years about how Korea's industries are ahead in this vital area because they, invested in technology and now have years of expertise. Anyway, the process of producing carbon nanotubes often leaves metallic particles on the surface. These impurities are catalyst residues, and one paper indicates this can actually make up as much of 10% of the material on the resultant nanotube surface. These impurities can cause electrical resistance to increase and can also create unusual semiconductor-like behavior, which is not something you want in a plain old conductor, and they can also increase junction resistance. Mechanically, these impurities can also reduce the carbon structure's strength, and they can make the final resultant nanotube less elastic, increasing their brittleness and making them more prone to fracturing. Basically, for this particular use case, these impurities suck. They can also be deliberately used to introduce aspects of these characteristics incidentally. If you're trying to make a carbon nanotube-based semiconductor, then doping with metal can produce the behaviours you're looking for. As another interesting aside to this aside, the catalytic metal residues in carbon nanotubes seem to be strongly linked to carbon nanotube toxicity. Yes, I'm getting in early before the misinformation. Carbon nanotubes are indeed toxic. Or at least we know carbon nanotubes with metallic residue are toxic. But do you know what else is toxic? Gasoline. Fossil fuel extraction. J.D. Vance's search history. The planet being on fire. So the first important thing that they did was to create a purification process for carbon nanotubes that selectively removes impurities that negatively impact electrical and structural performance. The process they've developed uses the liquid crystal intermediate state, a phase between when a material is transitioning from being a liquid to being a solid, where it has some characteristics of liquids, that is, it flows, but it also has some of the crystal structure that it will have when it solidifies. During that state, when the molecules can still flow past each other but are roughly aligned in the same direction, they use or manipulate the structure in such a way as to drive impurities out. That's because the lumps of metallic nanoparticles get in the way of a nice ordered structure, and the liquid crystals want, for complex physics reasons, to be in a low energy state. And a low energy state in this case is a nicely ordered structure. Traditionally, carbon nanotubes have been purified by a variety of processes. Acid treatment, which can damage the carbon nanotube walls and introduce more defects. Thermal annealing, which is energy intensive and which can also damage the carbon nanotubes. And magnetic separation, which only works for magnetic residues. So while there are limitations to the liquid crystal process for purification, this is a super important advance, and also potentially something that should be pretty scalable, because industrially, we've actually got quite a lot of experience dealing with liquid crystals. Alright, so that was the bit none of you were interested in. I made me interested, so I just made you sit through it because I'm cruel. The next bit is the bit that you came here for. So let's make you wait a little bit longer because, as we like to say, context is queen. And you came here to get depth, so depth is what I'm gonna give you. Back in 2023, there was a nice little review of research into the use of carbon nanotubes as a replacement for copper. Link in the down below as ever, and now on the TE website too. You did know about that, right? There's a link down there as well to our shiny new website. And the TLDR is that basically copper and even more so aluminium suck when used for transmitting energy when compared to carbon nanotubes. Copper, while it's an excellent conductor compared to a lot of other materials, is actually still responsible for around 75% of energy losses in what are termed electric machines. It also points out that copper is bulky, and as temperature rises, so does copper's resistance. In fact, for every 1 degree Celsius, copper's resistance increases by approximately 0.4%. A fact that's very upsetting if you're trying to build a performance EV, because as the motor and the wiring that's running to it gets hotter because you're pushing the performance envelope and ramming as much of that energy to the motor as you can, then the motor and the wiring to it increase in resistance. And what does that resistance do? Other than meaning that all that energy isn't going where you want it and requiring you to throw more to get the same result, it also makes the wiring get hotter, because as you try and shove energy through those increasingly resistive cables, they produce more and more heat, and the heat makes them more resistive, and oh no, we're in another vicious cycle. Now, we measure how well materials conduct in Siemens per meter. Blistering barnacles, you nautical nitwits! Not that kind of seaman! We also won't be hoisting the Jolly Roger on Regina's mighty shores, at least not today, because it's not that kind of seaman neither. Now, copper is basically the shiny standard material that hits the sweet spot of conductivity and price and weight. It's 58 millisiemens per meter. Aluminium, it's about 35 millisiemens per meter. Much worse, because with this, higher is better. Silver, which is a better conductor, but shall we say just a tiny bit more pricey. Today, checking, it's currently about 124 times as expensive as copper per kilo. It is about 63 millisiemens per meter. Carbon nanotubes have been clocked at 100 millisiemens per meter, making them able to do the Kessel run on less than 5 kilowatts. Please excuse the Star Trek reference. Okay, now I'm done making you all mad. Yes, I know, it wasn't Star Trek. Any nerd worth their Minbari salt knows that I just quoted Spaceballs. Carbon nanotubes are much better conductors. Now, how temperature will affect resistance is a bit of a question, because metallic carbon nanotubes and non-metallic ones, change in resistance is different. I would hazard a guess that they will behave like non-metallic ones, in which case their resistance might actually decrease as they get warmer. However, to be clear, even if it did increase, it's from such a better starting point conductivity-wise, that I'm not sure how much it will matter in the range of temperatures EV motors operate at. What about weight? Some quick and dirty figures pulled from the air. NASA's copper-carbon composite nanotube wires demonstrated approximately 50% weight saving, but that's for a copper-carbon composite. Pure carbon nanotube wires should be much lighter. Now, you're not going to see all of that weight paired out of the motor because motors aren't just wire. They're casings and spinny bits and connections and supports for the coils and cooling systems, but the vast majority of the weight is in the copper coils. Now, for example, the Bolt EV's motor and transaxle weighs about 170 pounds, that's about 77 kilos. Allegedly, Monroe and Associates' teardown of the Bolt indicated that approximately 22 pounds, that's 10 kilos of that weight, was motor windings. There is, to be clear, other copper in there, bus bars, connectors, but that 10 kilos could potentially drop by anywhere between a theoretically likely maximum of around 85% or as little as a probably initial 20%, which means that transaxle could drop by 8.5 kilos. Alongside which, while carbon nanotube-based wires do need cooling, and the motor needs cooling anyway for the non-widening bits like bearings, that cooling may be able to be lighter. Oh, you wanted that in pounds? Well, I'm a scientist and by training we don't use pounds. I have to give it in freedom units. Is that with or without the side of societal collapse? Okay, 8.5 kilos is just shy of 19 pounds, or about 0.008 large sacks for any Saskatchewan pirates still watching. Now, all this is years away, and we'll see incremental steps on the way there. If I was going to wave my finger in the air, I'd say we'll probably see 5 to 10% weight savings overall, at least at the beginning, not least because initial designs for carbon nanotube-based windings will probably be pretty conservative. Now, there's other neat ways this plays out. Copper is more than twice as carbon intensive as steel, emitting approximately 4 metric tons of carbon dioxide equivalent per metric ton of copper. Carbon nanotubes, ironically, could be possibly the only real use of the otherwise fairy tale that is carbon capture. Because we all know that carbon capture is the sweet forked-tongued lies that the fossil fuel lobby whispers into politicians' ears as they slip dollar bills intended for green technology out of government pockets. And there's one final possibility that's really quite cool. With the advent of 3D printing of metals, which, yes, is a thing that we can do, there's the possibility that we could just 3D print EV motors, and that is a future that's going to be pretty damn cool. Thanks for joining us today, and if you've got thoughts, make sure you leave them in our Discord room, on our Patreon page, down below, or you can reach out to us on Mastodon or Blue Sky. Thanks to the amazing list of people scrolling by on your screen right now. They're part of the massive community of supporters who make this channel possible, helping us through Patreon and YouTube, covering our bills, paying our team, and helping us to remain 100% independent. If you'd like to join them and see your name listed here and mispronounced horribly by me, just follow the links below. We've got options across a range of different price points from $1.50 US a month. A massive welcome to our newest supporters: Michael Anders, Tim Lynch, Kyriakos Keith Irvin, Eric Printer, Chip Chandler, Marek Kowalski, Thrill Nelly, Jake Alper, Howard Robertson, Dan Bow, Rex Baker, Bob F, Mark Brooks, Norman Davidson, Jean Lim, Lee Goldberg, Joseph Jarvis, John Taylor, Yaya, Kirabel, Jim Richard, Andrew Honeycutt, Lee W. Benjamin, and Hector. To join the list and get your shout out, become a paid Patreon member for your moment of fame, and you can even gift membership to someone else. If you'd like to support us with a one-off donation, you'll find links below to make Ko-fi and Bitcoin donations. And we even have an old-fashioned PO box you can reach us at, for the time being, addressed below. You'll also find links to our swag store, and if you're someone who has to shop on Amazon, please consider using our affiliate link so we get the commission, not Jeff Bezos. So we can continue to focus on making our content even better and reduce burnout, we're being a little freer with our release days, but plan on dropping new content every Tuesday, Thursday, and Saturday on our main channel, plus something on Sunday over on TE Take 2. If you want more, the algorithm that hates us thinks you should be watching this video, but this video is the one we'd like you to check out. Be kind, be awesome, be intentional, and don't forget to resist. Keep evolving!